All right, so we also talk about electricity in terms of power. In fact, most of our electrical devices are power rated, right? And we know that if we use an electrical device with less power, we then cost us less. It takes less energy. So how is power related to energy? And understanding that's going to help us really fully appreciate sort of this idea of electricity. So you might recall from Physics 1 that power is related to the work a device can do in an amount of time. So energy per time. Power, remember, is equal to the change in energy per time. Well, if I take that into terms of electrical energy, electrical potential energy, we can then write the electrical power in terms of my change in electrical energy per time. Now we also know from our voltage discussion, our potential difference, that the potential difference, our voltage, is the change in electrical energy per charge. Remember, it's normalized. The way we talk about potential is the electrical energy normalized to charge. So the potential difference is that change in energy per change in charge. I can use these two ideas to get a relationship for power in terms of the electricity variables that we've been talking about. So I'm going to rearrange this equation. I have V dq is equal to my D potential. And then I'm going to use that to rewrite my power relationship. So I'm going to substitute in V dq dt. And what do we remember about the charge per time? Well, that's just my current. And so power is related to the voltage and the current. Voltage times current. Now, we can use Ohm's law to get power in relationship to other things in our electrical discussion. These things we've been talking about: current, voltage, and of course resistance. So let's remind ourselves what Ohm's law tells us. Ohm's law tells us that the voltage is equal to the current times the resistance. It's the relationship between voltage, current, and resistance. So if I do a little bit of rearranging and substituting, we have three relationships for power that we can utilize in our analysis of electricity. We have the power equals the voltage times the current that we've already talked about. I can get power in terms of the voltage and the resistance by substituting in current from Ohm's law. So current is voltage over resistance, so I can substitute voltage over resistance, and I get the power as voltage squared over the resistance. Or I can utilize my relationship for voltage, and I get that the power is equal to the current squared times the resistance by putting in my current times resistance in for my voltage. So three ways to represent power that we can utilize to solve problems and to understand a little bit about how power relates to things that we experience in terms of electricity. So let's use one of them. We know that a 60-watt bulb is brighter than a 40-watt bulb. A 60-watt bulb is brighter than a 40-watt bulb. That amount of brightness is actually related to the current in a very simple circuit where we have, let's just say, a voltage source and our light bulb being the resistor. The current kind of gives us an indication of the brightness, or I should say the brightness gives us an indication of the current. So, what is the current through these two light bulbs? All right, well, a standard household outlet is 120 volts. So we're going to say we're in a standard household, which has 120 volts. All right? So for that standard household outlet, what is the current of my 60-watt light bulb? Well, if I'm going to look at my power relationship for voltage and current, I find that the power, 60, is equal to my 120 times whatever that current is. So what current does a 60-watt light bulb draw? A 60-watt light bulb draws a current of 0.5 amps. What about a 40 watt light bulb? Well, that's just going to be 40 equal to my 120 times my current. And we find that a 40 watt light bulb draws a current of 1/3, so 0.33 amps. So indeed, my 60 watt bulb draws a bigger current and uses a bit more energy, right? Charge per time. And if current is related to that brightness, then that 60 watt light bulb makes sense that it's brighter. Now, which one has the larger resistance? The 60 watt light bulb or the 40 watt light bulb? Well, we can use that same idea, but now using a different relationship for power. We can look at the resistance of the bulb using our power relationship. So if I look at resistance, if I rearrange my power equation for resistance, I get that the resistance is equal to the current squared over the power. So for my 60 watt light bulb, I have 0.5 squared over my 60 watts, which tells me that the resistance is 240 ohms. Now, do you predict the 40 watt light bulb to be a higher resistance or a lower resistance? Make your prediction, and then let's check it out. All right, so the resistance of a 40 watt light bulb is the current squared over the power. So that equals 0.33 squared over my 40 watts, and I get a resistance of 360 ohms. So, if you predicted it would be a higher resistance, you were right. And does that make sense? Well, a higher resistance in a circuit, based on Ohm's law, a higher resistance is going to have a lower current. And sure enough, our higher resistance has a lower current. All right. Now, when I was growing up, we called the electric company the power company, the energy company the power company. And the reality is we're actually paying for energy, right? What we get from the electric company is an ability to have these potential differences, these energy sources. So what I want to talk to you about real quick, just do an example, is how does the electric company determine how much electricity to charge us? Well, it measures it, of course. But how can we utilize the information about power to know whether or not it's worth maybe buying something and using it that has a very specific power rating? So, for example, you might have heard that, our LED light bulbs have a lower power rating, and for a long time, I'm not so sure about it anymore, but for a long time they would have this sticker on the box saying you could save X amount of dollars by using these LED bulbs. Well, is there some truth to that? How does the power rating relate to the cost? All right, so we're going to do a quick example as soon as I get everything erased here. I'm going to use a normal household voltage source, so 120 volts. In reality, our household voltages are actually in what's called alternating current, and we're right now talking about what's called direct current. We'll get to those differences a little bit later in our discussion. But for the most part, we're going to assume on average the 120 volts is as if it was 120 volts of direct current. So, almost done with this erasing. Get it nice and as clean as I can. All right. So let's do this example. An electric heater. It's summertime, so we probably aren't thinking about electric heaters at least right now, but if you're watching this in the winter, you might be. Draws 15 amps of current off the standard household outlet. So 120 volts out of that standard household outlet. If the electric company charges 12 cents per kilowatt hour, how much does it cost us to run that heater in the winter for a month for 3 hours a day? Only 3 hours a day. Maybe you'll appreciate why whoever you lived with said, turn the heater off or turn it down. All right, so how do we solve this problem? Well, what do we know? We know that the power of the heater we don't know the power of the heater. So we don't know the power of the heater. It draws a current of 15 amps, and we know that the voltage in the household is 120 volts. So we want to know what the power of that heater is to know how much wattage it's rated at. So we have our power relationship is equal to the current times the voltage. So this is a straight calculation, 15 times 120. It gives us the power of 1800 watts. Now we'll notice that the rate that the electric company charges is 12 cents per kilowatt hour. So let's put this in kilowatts so that we can get into a consistent unit, 1.8 kilowatts. All right, we want to know how much money it's going to cost me to run that heater every day for a month, 3 hours a day. So how much time is being used? We're actually paying the power company, the electric company, the energy company, and the amount of energy used per time. So how much time do we have? Well, we have 30 days in the average month. And I'm running it for 3 hours per day. So I'm using it over the course of the month, 90 hours. 90 hours over the course of the month. So what is going to be my cost? Right? I have 12 cents per kilowatt hour. I have 1.8 kilowatts of power being used for 90 hours. When I calculate that all, I get $19 per month is my cost. Not insignificant. That's $250 a year. Of course, you don't run it in the summer, but not insignificant. $19 a month to run that heater for just 3 hours a day. So paying attention to that wattage actually is going to help us out, right? The light bulbs of a LED light are rated at 4 watts versus 60 watts of their equivalent. It does save you a lot of money. All right. So example of power, thinking about energy per time. We came up with a few different ways that we can look at it to utilize it. A little quick example in terms of cost. Nice job.